Yeah, so I chose the title because Ray suggested it. Whether I don't know, maybe this is a bit like a field guide in the sense that you think about a bird watching guide that has pictures of interesting birds, and then you go out and you look for them. So this is meant to be sort of pointing at interesting things, and not some sort of intro how-to documentation thing. My expectation is ALCF users are still quite savvy, know how to use Google and whatnot, and so I'm trying to point at things that are a little bit more interesting than just the Hello World parallel stuff. Although I will use this. Yes.
I'm sorry to interrupt, Jeff. Do you have the ability to do video?
If you want, I haven't showered today, but
I see. Okay.
I don't mind. Hold on, just a second. I'll turn it on. I don't think I look hideous any more than usual. Sorry, let me get this back.
There we go.
Are you able to capture?
Yes,
both?
we see you now, and you look just fine.
Okay, I haven't gotten a haircut in a long time, but other than that, should be normal. Okay, so I didn't add my special disclaimer. Here's the one we have to do. I will add one personal disclaimer, which is that I measured these results. I'm a human. I'm fallible. I measured many of them about 5:30 this morning. So these are not official benchmarks. These have not been vetted by marketing. Please view them as the type of thing that is representative, but may in fact contain errors. Some of them have been debugged more than others. So please, please, please don't go out and cite this as official Intel hardware benchmarks, because I will then probably not be allowed to give talks again to public audiences. So this is background. Okay, so here's just an overview. This is particularly useful for the people on video to know whether or not they should click stop now. So I'm going to talk about KNL modes briefly. I'm going to show stream benchmark data, talk about cache versus flat mode, non-temporal store, tile versus core placement, affinity, and non-temporal store in Skylake, because that's obviously an interesting HPC product, even if it's not installed at Argonne in the big machines. And then I'll talk a little bit about something called PRK stencil, which I'll give details on later, because it's a slightly more interesting than stream benchmark. And I'll show both memory types and a little bit about affinity. And then I'll show some stuff with tasking models versus traditional OpenMP, because I think it's interesting from a application development standpoint. And then I'll talk a little bit about affinity and tasking in Skylake for just for contrast. So I'm not going to talk about how to use stuff or the hardware details. All of that is online on Intel websites and other places. I will provide a PDF of the slides, and I'll unhide some of the things. Basically, I have slides with shell commands that are how I ran stuff, which may be useful, but I'm not going to show it in the talk because it's incredibly boring. But I will provide that to ALCF. So I assume everybody's familiar with Knight's Landing, aka Intel Xeon Phi 7200 series. I'm going to use these simple pictures to talk about the memory modes and then programming it, and then we'll see the performance, which is where things get interesting. So flat mode is basically what we call it when you explicitly have the MCDRAM, which is the fast memory and small capacity, and the DDR, which is large capacity and lower bandwidth. Exposed. They're both independently addressable and allocatable, and then of course there's the cache hierarchy in front of them. You get, in this case, the largest capacity. You can get the best performance out of the memories, but you have to program it explicitly. And this, I think, is the bottleneck that inspires, I think, many of the HPC centers to run cache mode. The beauty of flat mode is you get total control. You don't have to pay any latency or cache pollution overhead associated with access patterns that aren't perfectly captured by what the hardware caching does. So cache mode is, of course, you use the MCDRAM as a cache. It's important to distinguish the difference between a CPU cache, which is what the L2 cache is, and what my colleagues call memory side cache. And they have different properties. So in a CPU cache, what happens is you do a load instruction out of memory. It moves into the chip, moves through the memory hierarchy, and it gets stored, and the hardware has magic for cache tags and coherence and snooping and all these things. When the cache is not part of the chip, it turns out that because of the huge capacity of this as a last level cache, you actually store the cache tags on the memory rather than in the chip. So what that means is there's a latency hit associated with going out and having to check the cache tags with memory in memory as opposed to in the CPU. So this is something, if you measure with a very fine-grained latency benchmark, the latency of cache mode is higher, and it's because of this implementation detail. Now, the nice thing about cache mode is you don't have to change your code at all, and you just get the MCD. If you have data locality, you get caching behavior, and if you touch something many times, it sits in MCDRAM and you get higher bandwidth. And you don't get the highest possible bandwidth, as we'll see in just a second, but it's a sort of good, easy button. And of course, you lose a small fraction of the capacity because you no longer have independently addressable MCDRAM. This is what I personally just called lean mode. It's not an official name, it's just a name I use. And this is basically, lean mode just means you have a workload that fits in MCDRAM, and you ignore the DDR, and you map your application into MCDRAM using NUMA control, as NUMA control -M0 puts it in DDR, and 1 puts it in MCDRAM. So this is just flat mode, but you ignore the DDR. And you have to map it explicitly with NUMA control because the default is DDR for a variety of stability OS and usability reasons. And the beauty of this mode is if your working set fits into 16 gigs, which it does if you run on BlueGene Q, and you can still use all the threads somehow with good OpenMP scalability, then you get really wonderful performance. You don't have to do any code changes. So it's the best of both worlds under the constraint that you obviously have a very small working set. This doesn't happen for most people, but it's the way I run a lot of my code that scales. Okay, so in terms of programming, I think I gave a presentation 2 years ago, or maybe longer, about more details on this. We have something called memkind. It has 2 levels of APIs. One is the lower level, which is the memkind API, which is complicated. It's a wonderful API. Doesn't appear that it's getting a lot of adoption because people just use cache mode. But I'm just going to show the easy button API, which is you take malloc, calloc, realloc, free, POSIX, memline, and you stick HBW, which stands for high bandwidth, in front of them. And this allows you to just write a C or C++ code where HBW malloc puts the data in MCDRAM if it exists as an addressable memory. Otherwise, it'll fall back or it'll fail. I can't remember which one. So you might be curious about how it all works. Underneath the hood, it uses a JE malloc allocator. There's a TBB malloc implementation too, I think. But if you're really interested in how it works, I wrote a really stupid knockoff called myHBW malloc, which I strongly don't recommend for production usage. It's not supported. I just wrote it for education. But basically, it uses DL malloc, mem spaces, and libnuma, and it's really meant to be an example of how you could write your own MCDRAM allocator if that was something that you wanted to support. There's really nothing magical about this. It's just that Memkind is high quality software engineering and uses JE Malloc, which is a really good allocator for threading. So just code snippets. There's
Jeff, I have a question. So do you need to be careful of what mode you're running in when you invoke some of these things in terms of conflicts, right? Do you need to be in flat mode, or what happens if you do this when you're in cache mode? Does it blow up? People probably...
The problem is I can't remember. I knew, but interestingly enough, all of the customer machines I use are cache mode, but the only machines I have internally are in flat mode. So I don't actually have a good way to sort of to test. And I use lean mode most of the time. So I believe, consistent with a lot of other things, this does not fail. So my understanding is the Intel software stuff is designed to be graceful and fall back as much as possible. This is, in fact, that graceful behavior is part of the reason I wrote my own, because people were having issues where they were getting silent performance degradation because of they did one thing wrong, and it would work, but they weren't getting high performance. So I wrote my version is either fast or crashes immediately.
Right, it's definitely an issue that if you are trying to do it one way and you don't get it, that you'd like to know where you're standing.
So my understanding is the ideal usage is you call HBW check available to know what you're doing, and then you make an algorithm choice if you need to. But I'm going to guess that HBW Malloc works in cache mode. It will just call Malloc, but I have not verified that.
So what you mean is it may just end up like any other Malloc in cache mode. In other words, you may end up in cache, or you may not if it's full.
Well, yeah. In the sense that if you're in cache mode, it'll allocate in DDR and it gets moved into cache when you touch it.
Right.
Per caching policy. So the other one I will mention here is 2 meg pages are a really good thing on KNL, and frankly in general, but they really help in KNL because TLB misses are expensive relative to bandwidth. And so having a page size explicit allocator is helpful. You need to have some kernel stuff, which huge TLBFS, or if you're on Argonne Cray machines, this is already really well supported in the Cray OS. So it may not be an issue for Theta, but in general, please pay attention to page sizes. So I'll show the C API is very simple. I haven't done anything to look at the C++ API, although years ago when I was making the first version of these slides, it was incoming. Please check for details. Here's the Fortran version. It's supported by the Intel compiler. I believe there's a Cray Fortran version equivalent, but I haven't used it. This is what I use in NWChem. So I work on NWChem sometimes, and I supported MCDRAM explicitly in kernels using this API. One thing that's very important, and it has to do with how the Linux kernel works and some other thing and binary formats. If you are having data which is bandwidth intensive, which likely is not present in C because you don't put huge arrays on the stack, but in Fortran, if you are the type of person who has a common block or an automatic array that's rather large, you need to convert this to a heap array in order to get it in MCDRAM. And this is it's a low-level issue. It's not related to hardware. It's not related to the user software. It has to do with the way that you instrument or describe the text and data segment of or data and whatever the other, basically the ELF format for the binary. And I believe Intel's got changes upstream to fix some of these issues, but just for simplicity, I'll say put it on the heap if you want to control where it goes. So summarizing what you should do, obviously the flat mode requires software changes, the others don't. The performance, DDR only is obviously, you'll get the latency, but the bandwidth is DDR. The rest are good, except note that there's this it's like 30 nanoseconds or something. It's a latency hit in cache mode. And then the capacity is obviously consistent. So, I think for the most part, people are here. And, some people are considering this. This is where I think this is the ideal place to live, but it takes a lot of work to get data to fit. This is the place where you don't want to be. Unless your code is truly bandwidth insensitive, just try to do anything other than sitting only in the DDR. But if you're in cache mode, you can't do that. It'll do it for you. So I'm going to go through stream. I've got two sets of data here. One is KNL data from 2 years ago, and one is I added one recent experiment. Is actually suggested by Jed Brown in response to the last time I gave this talk. But it's this. So this is note that I have got a power of 2 scale on the x-axis. That will change later. So note the shape of the curve is this curves because of that scale. It's more like linear on a linear scale. We see cache mode, DDR memory in flat mode, MCDRAM in flat mode. NT stands for non-temporal, also known as streaming stores. I'll talk about that in detail. So the trends we see here, this is on this part, I think on 64 cores, the peak bandwidth is 472 gigabytes. There's some dependency on the Linux kernel tick rate, so this maxes out about 490 if you do a bunch of tuning. The highest cache bandwidth in stream TRIAD here is 300 gigabytes a second, give or take. So there's a non-trivial difference in the peak bandwidth with cache mode. So it turns out, of course, if your application does a bunch of compute, your bandwidth sensitivity goes down and you might care less. But if your application is dominated by bandwidth, you should care about this pretty significant difference. And then the highest DDR4 bandwidth for 4-channel memory is obviously a lot lower, less than 100. Okay, so I'm going to point out a couple of key details here. So the first one is the non-temporal stores are worth a rather substantial amount of bandwidth. If you see red is MCDRAM non-temporal, and then green is MCDRAM temporal. So this is a pretty big gap of about 100 gigabytes a second. It turns out, in the case of stream TRIAD, the kernels are very simple. They're vector scale, vector addition, and memcopy like. The Intel compiler pattern recognizes those patterns. So if you write something like, basically anytime you write the equivalent of a memcopy, the Intel compiler will replace it with the intrinsic memcopy routine, which itself uses non-temporal stores. So the Intel compiler, this is just a compiler flag, and in fact the default will be up here. I have to do an option to disable non-temporal stores to measure this, but this matters because if the compiler doesn't recognize the idiom and generate it, you may want to say so explicitly or do some stuff like that. And then we see obviously MCDRAM is worth 200 and something gigabytes a second. Now the other part that's interesting, you see, cache mode is less than the temporal store version of MCDRAM. So you're really paying a pretty significant penalty if you're not exploiting both MCDRAM and in flat and non-temporal stores. And I will say there's some very small, not source code modifications. I think I have to align 2 meg pages. So if you look on GitHub, I've got a fork of the stream benchmark where I make add the attribute for alignment, and then I have the compiler flag. So if you really want to reproduce this, see there. This is also important. Is bandwidth. The bandwidth differentiation only happens once you're using enough threads to hit the bandwidth limit. If you're running at low concurrency down here up to 8 threads, you're not actually able. Your ability to move data is limited by the core's ability to issue load store rather than the memory controller. So this is an important fact that if you're OMDAL limited, if you have a code that's doing a lot of fork join OpenMP, and in between you're doing mem copies, you may not notice on Xeon or on older versions of Xeon especially, but on KNL that code really does need to be parallelized. You need to parallelize almost everything, if only to saturate bandwidth. This is something Jed Brown and I were talking about a long time ago, and I did the experiment. This is the difference between placing, if you're underpopulating the node, the difference between placing a thread on every core versus every tile. So if we look at, this is 68 core part, that's 34 tiles of 2 cores each. If we look out here, if I run 34 threads on this, I can either do the first 34 cores and place them on 17 tiles, or I can place a thread on every tile on the first core of every tile. And this has a pretty big impact on performance. You see here, if you look at TRIAD, which is the lower number, the higher number is stream copy. So stream TRIAD is 390 on 34 tiles, and stream TRIAD is 257 on 34 cores. So the important thing here is that the bandwidth scales in proportion to the number of tiles you're using. You do get a little bit more bandwidth if you look at going from 34 tiles, 1 core to 2 cores. You do get a boost, obviously, because 390 is less than 472. But this is something that's really important if you're underpopulating your node for part of your code, such as if you're running MPI and OpenMP together, and at some point you are doing some data movement only on your MPI and not in a threaded region. You'll want to make sure you spread your MPI ranks out properly. It's likely that a good MPI stack or Cray AP Run or Cobalt or whatever it is or Slurm, whatever you're using, will do this, but this is something to check out. There's a whole lot of documentation about the affinity controls and for MPI and OpenMP and schedulers, so I'm not including that here. The other thing, this is a linear scale. You see the bandwidth is basically linear all the way out until the very end when you start to saturate the memory controller. So if you're bandwidth limited, use as many cores as you can because you'll get more bandwidth for it. Now, just for contrast, this is Skylake. This is the most expensive or the biggest, most capable Xeon chip. So this is it's a 28-core part. The 2-socket system, I'm showing a 1-socket and a 2-socket result here. The peak bandwidth, this is a 6-channel DDR4, so it's the peak on the 2-socket system is 201 gigabytes, I think. It might be a tiny bit higher if you're smarter than I am. But it saturates at 20 cores, which, if you're wondering, your peak LinPack happens at 28 cores, peak deep learning happens at 28 cores, but your peak bandwidth happens at 20. So some of the HPC folks might be interested in the 20-core SKU just because it's balanced in that sense. We see here there's a very small impact from affinity, and I learned this the hard way because I was confused about why the bandwidth out here at the max was not what I expected. And this is if you run the threads in scatter, which means you sort of stripe them, versus compact, which is contiguous placement. you see a small difference. It matters if you're benchmarking stream. It probably doesn't matter in other workloads. We see a benefit of non-temporal stores that's rather significant. This is, of course, about 200, and this is about 160. So we're talking about 10 or 20% difference from non-temporal stores, which, again, in this workload are generated by the compiler. We see the same benefit. This is roughly, a factor of 2, so the bandwidth obviously scales in the number of sockets. Again, your core limited in your bandwidth up to a certain amount of parallelism. Obviously, you only need about, you start to see the difference around here, but then you saturate up at about, or get close to saturating about 12 cores. So you definitely want to be using about at least half the cores if you're moving data. So you got to parallelize those loops. So again, the NT is non-temporal. WB stands for write back, or RFO if you're, depending on what type of person you're talking to. This is the default x86 store. So non-temporal stores are an extension. They've been around for almost 20 years, but it's not the default because it has a weaker memory model. It's actually, non-temporal is more actually like the Blue Gene PowerPC store. So there's some funny things where you change your code to depending on which machine you're on. So summary of this stuff, KNL performance, obviously MCDRAM is the best. Cache mode is a little bit worse, but still better than DDR. Programmability, they're all the same up to 16 gigs, and then beyond that, obviously, you care about the difference versus flat mode. In both architectures, non-temporal stores are important. Pretty significant difference. I think this is relatively new. I think I looked at non-temporal stores many, many years ago and didn't see anything interesting. So if you're running things like matrix transpose, moving a lot of streaming data, you care about this. And you really need parallelism to saturate bandwidth. Obviously, if your laptop probably gets most of the bandwidth out of a single core, but in a server part, you really need parallelism if you're moving data. So just because it's important, because the compiler will not always do this for you, programming non-temporal stores, there's an Intel pragma where you do vector non-temporal. This has been around. There's an equivalent in our Fortran compiler. I think it's dir vector non-temporal. There are Cray and PGI equivalents. I found them in the user manual. If someone cares, I'd be happy to share them. But PGI doesn't support AVX 512 yet, as far as I know, so it probably doesn't matter. This is something new. You will not find this in any implementation yet, but we, as in Intel employees, including myself, got this added to OpenMP 5. It's a very small change, but it's nothing more than the OpenMP standard version of this. So this will presumably actually be supported in GCC at some point, which will be nice because GCC doesn't have non-temporal yet. And then if all else fails, you can write intrinsics. You can, of course, write assembly, but that's less pleasant. This is the AVX 512 intrinsic syntax, but there are other versions going back to SSE. One thing I will add is very, very important, and there are low-level Linux programmer types. We'll say if you ever see streaming load store and the epoch is not closed by an S fence, the code is wrong. It may not execute wrong every time, but it's definitely capable of being wrong. This is because non-temporal stores are not necessarily ordered or completed in the same way that write-back stores are. And so if you issue a bunch of streaming stores in a function, return from that function, and then go load that data, you may not see what you think you would see based on the x86 memory model. So please remember, if you're going to use these instructions, you got to have an S fence there. Very important. And intrinsics, of course, work with ICC, GCC, Clang. I don't know about anybody else, but they definitely work with GCC. So this is the end of the stream section. So if there's questions specific to stream, please ask them now. Okay, so now I'm going to talk about Parallel Research Kernels. This is the GitHub link. There's all the source code, a whole lot of fun stuff there. That I'm going to be basing this off of the C++ versions, but I have written the same code in many, many programming languages. So just as an overview of the project, in case it's not relevant to the specific aspect of the talk, but I want
Jeff,
yes, Rick.
Sorry to interrupt. There was a question on the chat. What branch of the stream fork was used for the work?
I used the KNL fork or KNL branch for the KNL numbers. I have a branch that is derived from the KNL branch, which has the Skylake flags, which is in GitHub. So there's a KNL branch and an SKX branch. Those should be the right code. But like I said, the only thing I did is add 2 meg alignment to the pointer, and then change the compiler flags. So, and please, my email is very easy to find. If you have any questions or concerns, please email me, because I want to make sure that the data that I present is as reliable as possible. And of course, all this stuff is on GitHub. So the point is, if you don't like it, please fact check it. There's nothing hidden behind the curtain here. So Parallel Research Kernel is, I work on him quite a bit, so I just want to give a brief overview. It's an implementation of some HPC patterns. It's sort of smaller than a mini app. It's more of a micro app. We have a stencil kernel, transpose. We have a derivative of stream triad. It's just stream triad, but it's then we have something wavefront. We have all the way out to particle and cell proxy. So it's not a particle and cell code. It's just a code that does the same things at a low level. And we've implemented these things many, many, many different ways, all sorts of different languages. I've been working mostly on C++ recently, but we have different versions, Python, Julia. Even the Rust ones are terrible. It's how I learned Rust, so they're probably the worst Rust code you've ever seen. But we do have Fortran 2008, just as a contrast. And then we have a lot of programming models. The C++, and actually all 3 of these support OpenMP 4.5. There's TBB, OpenCL, a lot of stuff with modern C++. That's not really what I'm going to show here, but since ALCF people are pretty smart and curious, I thought I'd mention it. These are all flexibly parameterized. They're not benchmarks. They're just meant to be tools for experimenting. Nothing is tuned. So people who do stencils for a living have looked at my stencil code and said, oh, that's totally trivial, you're dumb, or whatever, because I don't block for cache or write all the vector code or do all the crazy ninja stuff. But that's not the point. They're really meant to be reference kernels. And, if the compiler does a good job, that's great. And the other part is we try to use things idiomatically, meaning the right way to write OpenMP or the right way to write TBB, as opposed to, some maybe what's popular, which could be wrong, is often the case with OpenMP. So this is the Python pseudocode, or this is the Python implementation, which is the pseudocode for how we implement this. So the stencils are quite simple. This is 2D. The reason it's 2D is because it makes it slightly simpler to write, and it emphasizes non-compute. So we care about things like synchronization, and in this analysis, the 3D is more interesting if you're going to tune stencils, of course. And I'm using radius 4 because that does more flops and therefore makes it slightly more interesting. But these are constant coefficients. So if you're a geophysicist and you don't have a constant coefficient RGM kernel, you probably wouldn't like this, but this is just a proxy. So I have 2 different versions of OpenMP, which I'm going to show for a variety of reasons. OpenMP traditionally is very good for regular workloads, but if you have something with load imbalance and you're not going to write your own load balancer, it can be helpful to write in a task parallel motif. Task loop in OpenMP has some nice properties with composability as well. but as we'll see later, the performance is not ideal, at least relative to the max you can get with regular OpenMP. Question?
Yeah, Jeff, there was a question. It may be from a little farther back.
Okay.
Do the Pragma OMP non-temporal directives force the code to use non-temporal stores, or is it only a suggestion? And is there a way to check that the non-temporal stores were used, like in a compiler optimization report?
So I would expect the opt report to say yes. I know that if you put Pragma Vector or Pragma OMP SIMD, the compiler treats that as a directive or a command rather than a polite hint. So non-temporal, I believe it will generate if you tell it to, unless it sees a problem. But I have not, I can't say unambiguously that I've looked at enough opt reports. Both opt reports and assembly output are the way to verify. But in general, the way the Intel compiler treats these things is, unless they really look like a hint, such as suggestion about how many a loop trip count, it tends to be prescriptive. But I think it's very important to check the opt reports to see, because I think if you generate a non-temporal store for a loop that's going to store to L1 cache all the time, and the compiler knows that, it may not want to generate non-temporal stores, but I don't know whether it will do it anyways. So just showing that the red and the blue, by the way, these are exclusive. These don't write the code this way. The same version is blue one way and red the other way, and then they both contain the purple code. And this is I do two-dimensional tiling on the stencil, and I'll talk a little bit about why it's obviously a basic optimization. But in contrast, this is the TBB version. And for reference, TBB is open source, it's portable, I found a bug. It doesn't compile with the Cray compiler, but it compiles with most of the rest of them. It runs on ARM, it runs on Power, and they switched from GPL to Apache, so it should be friendly for anybody to use for anything at this point. Historically, people have objected to TBB because they think it's Intel proprietary, and it is certainly not. So this is TBB Parallel 4, which is nice in that it actually will generate the blocking. So I can generate a block two-dimensional iteration space automatically, and then behind the scenes it will do some stuff. And then the partitioner here I use an Affinity partitioner, which tries to schedule tasks with Affinity. So this is brief hardware details. I use the latest compiler. This only really matters if you're going to reproduce this stuff, so I'll skip it for now. At least one important note with Skylake. This is in Intel 18 compiler. There's something called Core AVX 512, which generates AVX 512 for Xeon, but with the ZMM equals low flag. And that is because the frequency will drop when you use the widest registers, and unless you're using them very effectively and your code is very compute intensive, it's better to actually use the 256-bit registers, the YMMs, which is what this will do. And that's what I do because I don't think my code has enough flops to justify the frequency drop. There's just enough memory dependence. But there's some Intel blog posts about this. So these curves, these lines, right? These are just to help your eyes. Do not assume this is interpolation. I found the dots too small, so I added the lines. But I know there's people who think that that's bad. So this is KNL showing the stencil, and I show two forms of affinity. I'm running on all the threads, and with NUMA control. So this is DDR, and I didn't even bother with affinity because it's clear that DDR is bad performance here for across the board. And then we see If we just switch to MCDRAM, that's the light blue line, performance gets good. And I added the affinity, so the light blue doesn't have just uses whatever the runtime does automatically, which I assume is relatively good because the workload doesn't move around. But we see here that there's some variation with compact, which versus scatter, and this is partly because if you think about how thread IDs are assigned, if adjacent threads touch the same data, you want to schedule them next to each other so that they'll get cache reuse. So you see some benefit for the smaller problem size when you use the compact ordering. However, probably here it drops a little bit because now you're sharing you get cache collisions and then you get more cache reuse. And so, anyways, these bumps are merely to show that affinity causes differences, and it's worth using them to see what the best behavior is for a given workload. But it's really problem size dependent, and so there's a right answer. In general, I use scatter when I think that the bandwidth is more important, where I use compact where I think cache locality is more important. Now I'm going to show, so best is just the I believe it's this one, the orange line, M1 so MCDRAM with compact scheduling I pulled over here. Now I showed the tasking stuff because people are often, people may have heard, oh, task-based runtime systems are the future, everything else is terrible. I've heard people talk that way, and I've also heard people say, oh, task-based runtimes perform worse and you shouldn't use them unless you hate performance. So I've totally hysterical, outrageous opinions on both sides. So I measure them because that's reality. And so we see here TBB and task loop with OpenMP, both of which will do some form of dynamic scheduling. DDR, obviously, they both perform bad. Don't use DDR and KNL. You can avoid it. And then we see here task loop and then TBB. And so the interesting thing here is, first of all, TBB is asymptotically better. I haven't root caused that. I think it has to do with the caching. But TBB hops up pretty good for the smallest problem sizes. The task-based scheduling is some overhead. But once you get to about here, the difference is relatively small. And I'll show in just a second why this is actually quite a nice result because I didn't have to do any work to get this. The old version was back when I first wrote the OpenMP code, and I compared to some other things, but that's not relevant. I saw this number and I was like, this is crazy. Why is TBB doing so well? And then I looked at the code and I realized, oh, well, I'm not doing two-dimensional tiling of my loops. I just wrote parallel for and went through the whole domain linearly. And of course, that's a great way to hit the bandwidth limit. So what you see here is if you write dumb code, but you use TBB blocked range, it'll just take care of it. Whereas what I did to get from here back here is I went through and I had to apply 2D blocking to my code. So this is something where you can view it as you have to do more work to get the right answer or the right performance with OpenMP. But if you do the work, the performance is better. If you don't do the work, you may be losing out on something versus a higher level model like TBB. Same thing on Skylake. So this is just showing this is no affinity down here. So this is 56 threads with letting the runtime do whatever it wants. Light blue is 1 thread per core, but telling it with affinity. And then yellow and orange are 2 threads per core, and then whether you number them contiguously. So we see that compact is the best, obviously, because if you place the threads adjacently when you're talking about hyperthreads, they're gonna get L1 locality and share data. Versus if you don't, that's worse. And in fact, for the smallest problems, you see a pretty big difference. This big bump here is because everything fits nicely in cache. And then as you go down here, things are not fitting in cache. I suspect that if I was smart and did a good job with cache blocking, I could get these numbers up quite a bit. But then I'd have to be putting cache size parameters in my code, which at least in this code, I'm not doing. And now showing the tasking stuff. Here I showed different task granularities. Turns out on KNL, the task doing grain size, which is how many tasks you assign to a thread at a time, was very bad, so I didn't even include it. But we see here that amortizing the task scheduling on Xeon is a good idea. But we see here that the best OpenMP with Affinity is winning by a decent amount. TBB here is relatively low and then comes up. I think a lot of this has to do with the fact that I was running on 2 sockets. If I localize the thing to 1 socket, TBB will behave better because doing task scheduling across NUMA is not ideal. Actually, yes. So this is the end. I didn't have time to write the summary slide. So just to sort of recap here, the goal was to talk about the difference between MCDRAM and DDR from programmability and performance. We saw that with Stream Benchmark. We see the relatively significant differences with both, obviously with MCDRAM and then with non-temporal stores, and then we saw how to program them. And then we see for a relatively simple HPC proxy like a 2D stencil code, we see obviously there's a pretty substantial benefit from MCDRAM because the code is saturating bandwidth. And we see that Affinity has the small but noticeable impact, and that task-based runtimes for task-based scheduling can be useful, but has some overhead, and that one has to be a little bit careful about tasking granularity. So I've done a whole bunch of study with this that doesn't fit in the scope of this talk, where you can obviously rearrange these lines quite a bit if you go in and tune the knobs. But it's important to see tasking not as a direct competitor to OpenMP Parallel 4, because if you can use a statically scheduled for loop, just do it. But if you have something like an AMR code or some sort of a stencil with an inhomogeneity term, or a term that only applies in portions of the grid and not others, you may not want to use a static schedule, and that's where the task-based stuff comes into play. And I've certainly seen in other contexts where things like TBB, which does hierarchical work stealing, can do substantially better than statically scheduled loops without really introducing any programming complexity. So I'm going to drop out of full screen mode so I can see the chat if there are any questions. Everything, any questions?
There was another chat question. Let's see. What are the best settings for Affinity when you're saying best in the? I think in one of the charts.
Yeah, best is just usually it's Affinity, turning on Affinity with compact. In this case, it's pretty much the best across the board. For this one, I chose best. Obviously, it's not unambiguous. There's variation here, but you could tell from the shape that it's I just chose compact scheduling. So, and it's not best as a way of saying this is the best mode, please use it. It's just saying I only wanted to pull one line from one plot to the other to keep it readable. But if people are interested in this stuff, I have a scripting harness that actually generates all the data with all the settings with all sorts of different knobs that I'd be happy to share with anybody who wants to study this in more detail.
So I think a general question, I'm wondering if you have any perspective to share on this, is that, the current KNL, has 16 gigabytes of the high bandwidth. RAM. But, of course, other machines in the future may have different amounts and so forth. And so what is there a good defensive programming strategy so that you don't have to redo your whole code for every machine?
That's a tricky one. So, the cop out answer is use lean mode, which is tune the thread scaling of your code like crazy and the MPI scalability, so that regardless of how small the fast memory is, you can fit. 16 gigs is presumably the lower bound at this point. GPUs have 16 gigs. I think Volta has 16, and they just have a follow-on 32. I can't talk about Intel future products in this context, but we generally don't regress in user experience. So 16 gigs is a reasonable starting point. One should not expect fast memories to grow very quickly. I spend a decent amount of time thinking about economics, certainly more than I did in DOE. HBM is expensive in a variety of ways. It draws a lot of power and it costs a lot of money. And so one would not expect, and also in order to get HBM to work as a high bandwidth memory, you have to glue it into a ceramic package. It's not like you don't have HBM DIMMs. Which limits capacity. And so I would not expect, 384 gigabytes of HBM in the near future. So what people really need to start thinking about how they compress their memory footprint to fit in high bandwidth memory. I also try to say this the right way. Cache mode is not a panacea, and it is very difficult to implement. And as I showed, there are some significant overheads to doing it. As popular as it may be in today's KNL systems, I would discourage people from relying on cache mode as the solution. You can't just say, oh, well, I'll always have cache mode, it'll always work, I'll just use that. I think it's really important for people to either do lean mode or to do the explicit stuff, even though that requires code changes. I think the hardware agnostic way of viewing flat mode with explicit support is thinking in terms of hot and cold working sets. Certainly anybody who's doing GPU offload programming has already thought about this, because if you think about KNL, it only has one processing element, but it has one big DDR memory and one fast memory. And a GPU-based system has one big DDR memory and then the GPU memory in separate address spaces in non-coherent way. You have to explicitly copy between them or allocate locally in Scratch. And it just has two compute elements. So KNL is sort of half of the complexity of a GPU offload model. But it's certainly something that if you want to be performance portable to all the DOE machines, thinking about the two memory spaces and two compute spaces is useful. KNL, you don't have to worry about two compute spaces, but certainly if you factorize your code the way you would for a GPU, you should very easily be able to support that. Just do HBW malloc in place of CUDA malloc. And things should behave.
So your recommendation of either going lean or going all out to do everything explicitly in flat, what's conspicuously absent is any mention of the hybrid modes. Do you think that they're more complicated than they're worth for the benefit?
Well, so I deleted those off that slide because my impression was no HPC center had enabled hybrid mode. If somebody is, then I guess for me, hybrid mode is just a linear combination of flat mode and cache mode. So you can pick and choose. Okay, interesting. So yeah, I think the thing I don't like about hybrid mode is as the cache shrinks, it becomes less useful. And if your flat memory is smaller, then that also becomes less useful. So if you could go into hybrid mode dynamically in every job and it costs you nothing, and you could choose any arbitrary division of memory, then maybe it would be useful. But I wouldn't bother thinking about it. I just figure flat. Let's see. C++ vectors STL. This is an interesting topic. So I've gotten involved in ISO C++ more recently. It turns out STL vectors don't support NUMA. And it has to do with, or in the sense that you have to have the trivially constructible initialization thing. And this means that you can't use it. You don't want to use the STL vector on 2 sockets, and you can't rely on Linux First Touch to fix it. This is where you'd want to rely on a custom allocator. J.E. Malik in Memkind TBB, I think, should solve this. I think it's an interesting discussion. The other one I'll note is, things like Cocos and Raja are trying to be sort of C++ abstractions here. And I didn't show any of it at all, but my experience with Cocos and Raja in the same experimental context as we showed here is actually quite good. They're zero overhead, and in some cases they beat OpenMP because they C++ magic insert some things that actually help the performance.
Going back to the hybrid mode issue, someone on the chat comments that DoD has some hybrid machines set up with hybrid mode.
Yeah, I get why they probably do it. I wouldn't do it, but then again, I wouldn't use cache mode, and nobody listens to me in DOE.
It's the path of least resistance.
I know, I get it. So is Fortran 77 if you're, So anyway, so by the way, please email me, the person who asked about Wavefront. It's basically it's a derivative of the pattern that you'll see in Snap with loop carried backwards dependencies, which are intrinsically hard. But I've done a lot of work there. I'd love to talk about it, but it doesn't fit because we're at 11 and it's different from what we're doing here. Oh, sorry. There's let's see, ADI. What's for memory bound? Okay. Okay, MPI versus OpenMP breakdown. That is a very, very tricky one. And I think the answer is probably determined mostly by Amdahl's law rather than anything particularly specific. So I'd say first part is find the Amdahl sweet spot. Second one to deal with is on KNL, depending on your network, you may need many MPI ranks up to 16 to generate the right injection bandwidth. So if you run 1 MPI per node and you're on certain networks, you will not get anywhere near the peak MPI performance for messages that aren't huge. In contrast, if you do a bunch of MPI per node, you'll probably do a bunch of send-receive copying between cores, which is not ideal, and you'll waste all the memory on the halos that you wouldn't have with OpenMP. So I have studied this a little bit. We have a version of this benchmark PRK where we have that implementation. We've studied it. But I guess as just one example with NWChem, the version of the code or the module in NWChem, which is very well threaded now, Eric Belaska did a huge amount of work. We actually run 1 MPI per node because the threading scales really well, and using more than 1 MPI rank doesn't improve anything because you start paying MPI send receive tax within the node. But that's only true that it works that way because the thread scaling is good out to all the 68 cores. Most codes that I've seen do not scale that well in OpenMP.
Are there any other questions before we wrap things up?
Well, let me take the question off the chat. So, both good questions. So on Cray machines, Aries is an offload RDMA network, and my impression is it saturates message rate relatively quickly in the number of ranks per node. I have not measured that in years, so I don't want to say. I'm gonna guess probably 4 or 8 is pretty good. You shouldn't have to go higher than that, I guess, but it depends on how big your messages are. If you send 20 megabyte send receives, you probably do fine at one thread or one rank. If you're doing 8 bytes, you need a lot of them. So I would just write a benchmark to figure out where the saturation is. SNC versus quad is a very, very important question. At least in KNL, the performance benefit of sub-NUMA clustering was very, very small. It was almost immeasurable, while at the same time allowing the programmer to absolutely screw themselves with terrible affinity and NUMA issues if the MPI process launcher didn't do the right thing. So our early experience with this internally, people had to work really hard to use SNC, and some of them were able to observe a pretty small benefit. So if you care about 5% or something on that order, it's worth doing. In some workloads, it may be immeasurable. What I will say is that, and there you can actually do SNC2 on starting in Haswell, just nobody turns it on. It's called COD, cluster on die. Without being specific, SNC is going to grow in importance in the future because scaling on-chip networks and various things about memory interfaces is hard. So, it'd certainly be productive for people to think about that. However, of course, if you're an MPI user and you have 8 MPI ranks, you're assuming your MPI launcher does the right thing. You will be fine trivially with SNC 8, or basically SNC up to the number of MPI ranks, because you would do 1 MPI per NUMA node the way you would do on a multi-socket system. The only hard part about SNC is if you want to now scale shared memory threading models across it. That's where some of the tasking stuff starts to become interesting, because traditional OpenMP does not scale in NUMA because for a variety of reasons, mostly related to Linux First Touch. But if you are smart with how you use tasking, you may be able to solve some of that. So it's a very important question for the future, at least in KNL and Skylake. There are small benefits to SNC style modes, but they're way less important today than things like non-temporal store and the like. So we're over time. Please email me. It should be easy to find. You can go on my GitHub page and find my Google Mail, or if you know my Intel mail, you can use it. Yeah, all the stuff's on GitHub. Please email me, ask questions, download the code, and I'll try to answer questions as soon as I can offline.